In the previous video, we defined polynomial functions and talked about some important terminologies, important lingos. It's difficult to use the terms that was not already taken over by some mathematician already. I cannot use the term anymore because this kind of thing is term now. Well, some pun intended. Okay, and then we talked about remainder theorem and factor theorem. I explained the reason. However, as I told you, using remainder theorem and factor theorem are rather impractical. I told you a much better way, that is to use factor command. Factor, and then, for example, if you want to factor this polynomial down here, then well, I'm using copy and pasting, but you can always type in. And then you're going to have factorization like this. Using computer algebra system, you can factor any polynomial very effectively. You can do something very similar with Wolfram Alpha. We talked about those. Now the technical part is now done. So let's talk about what do we do after factorization. Let's talk about the theory behind it. And let's answer those kind of questions using this problem here. 2.5a. I could have used 2.5b or c, but they're more complicated, so let's stick to the simplest one. Determine the nature of each zero of the given polynomial function. And there are three zeros, as you can see. The first factor, 2x plus 1, is equal to 0, so I get a 0, x equal to negative 1/2. The second factor, x minus 1, is equal to 0. So we're going to get x equals to 1. That's the second 0. And the third 0 will come from the third factor. 3x minus 2 is equal to 0. So I'm going to get x equal to 2/3. And at those three zeros, at each 0, we want to find out the local behavior of the graph of this function. Now, how does that work? Basically, what I'm going to do is I'm going to introduce you similar but a little bit different function. Similar, a little bit different, but much simpler function. How do I do that? At x equals to negative 1/2, keep this factor as is. And to the other factors, plug in x equals to negative 1/2. Pretty much like this. So we have three zeros here. At x equals to negative 1/2, keep this factor as is, and then substitute x by negative 1/2 here and then there. So what we have, we ended up changing my function a little bit. So it's not the same as the original function. And another thing is, this new function is simpler than before. The original function has, well, let's say second degree, one more, and then three more. So it was sixth power function. Not sixth power function, excuse me. It was a polynomial function of degree 6. But this one is a polynomial of degree 2. So it's a lot simpler. All this part is just a number. And then we have 2x plus 1 squared. And then the behavior of 2x plus 1 squared is actually easy. It's just a power function, shifted a little bit, and then some stretched a little bit. So that's not too much of a problem. Now, why are these two functions behave similarly, not the same, similarly around x equal to negative 1/2? Because x is very close to negative 1/2. It says around x equal to negative 1/2, right? So when x is close to negative 1/2, replacing x by negative 1/2 will not change too much. That's why we just did what we just did. Replace x by x equals to negative 1/2. But if I do that to this one, I'm going to lose all my information, because if I plug in x equals to negative 1/2 here, then you're going to get 0 times something. Everything is 0. Then you don't really get anything. Now, let me show you a graph. Actually, two graphs. The blue graph you see is the original function, graph of f. The red one is a graph of g1. And as you can see, they are two different graphs, but they behave rather similarly around x equal to -1/2. Let's zoom this a little bit further. Instead of drawing this from -1 to 0, draw this from -0.6 to -0.4. And what do you see? The blue and red are behaving a lot similar. They're closer together. And then of course, if I go even further, then they are now virtually indistinguishable. So there goes the graphical justification. Theoretical justification we already did, and because x is not equal to -1/2 but very close to -1/2, replace x by -1/2, we're gonna get not the same but something similar to the original function. But we can't do that to this one, because if I do that, I'm gonna get just 0 and nothing. So what kind of behavior does this graph G has? This part is just a number, so it's simply stretched or flip-flops, nothing much. What we have is just a power function of degree 2. That's a parabola. So the graph of the original function, just like graph of this G1, behave like parabolic graph, touches the x-axis and then bounces back. And that's the same for any even power function, any even multiplicity. Now, what if we want to find out the behavior around the next zero, x equals to 1? We do exactly the same thing. X minus 1, we have to keep this one, because if I substitute x equals 1 here, then 1 minus 1 is 0. I'm going to multiply by 0, and then I just lose everything. Everything's 0. But other x's are okay. Substitute x by 1 here and there, so we get a different function, a lot simpler. And because x is very close to 1, the behavior of these two functions will be similar. Not the same, but similar when x is close to 1. As you can see, we have something like this, and the red graph is the graph of G2, and that's a linear function, isn't it? This is just first order. Oops, let me highlight. This is just first degree, so it's a linear function. So the graph of the original function, the blue one, behaves more or less like the linear function, kind of like a line. It cuts through the x-axis. So we have a sign change. The left-hand side we have negative, right-hand side we have positive. Depending upon the sign, the slope may be negative. In that case, positive, negative can be changed. But then again, the nature of linear function, that doesn't go away. You have cutting through, kind of like this. So we have to have a sign change whenever we have first degree. Multiplicity 1. How about some other multiplicities, some other mod multiplicities? Well, here's the third example. Around x equal to 2/3, replace x by 2/3, and we're not going to change anything. Excuse me, we do change, not anything. We are not going to change too much because x is pretty close to 2/3, but not too much. We'll change, yes, not the same, yes, but similar. And here is the graphical justification. And okay, I think I just zoomed too much. How's that? Maybe a little bit further. Zoom out a little bit. Okay, and let's look at the blue graph and let's look at the red graph. And then the behavior of the red and blue are, as you can see, very different because we have relatively large viewing window. But around x equal to 2/3, they should be the same. Not the same, excuse me, similar. So let's zoom in further. And then as you can see, we have very similar behavior, blue versus red. And red is the power function of order 3. So it behaves like cubic function. It cuts through the x-axis, but not like linear function, just straight cut, but it's kind of warps and then eventually crosses the x-axis. That's going to be the case for any odd power. So any odd multiplicity, because of that kind of local behavior, we have sign change, and the graph crosses the x-axis. If you have even multiplicity, then because of this local behavior where the graph of this function hits the x-axis but bounces back, we don't have sign change. In the end, we have this kind of conclusion. And at 2/3 and 1, we have odd multiplicities, and x equal to -1/2, we have even multiplicity. So the graph of the original function hits and bounces back around x equal to -1/2, consequently no sign change. But around x equal to 2/3 or x equals to 1, the graph crosses the x-axis, so we have to have a sign change. Let me see, do we have real graph here? Kind of like this. It's kind of difficult to see, to tell the truth. So just blindly using your calculator to figure out probably will not work very well, just like this example. I think I intentionally designed it that way. 2/3 and 1 are pretty close to each other, so unless you really zoom in around 2/3 and 1, you are not going to see any interesting behavior on there. So you really have to use your brain. And this kind of diagram over here is, of course, the conclusion, but the reason behind all those diagrams actually coming from these kind of estimation and local behavior given by related similar functions. There are three such functions, g1, g2, and g3, because we are considering three zeros. And g1, g2, and g3 will behave very similarly with the original function f of x, only when we are zooming in pretty close to the corresponding zeros. If you go far away, then they're not going to behave similarly at all. How about the other problems? Well, you can answer pretty much the same thing. I didn't draw all those this reference graphs for B and C. So even if you open up and do you see those how many? 1, 2, 3, 4, 5 reference graphs? No, I didn't draw any of them. I just gave you this diagram and then a graph of the original function, which is not telling you too much. It's not really informative, and it is kind of designed that way. And you cannot just use your calculator and then read through and then answer the question. You really have to go through use your critical thinking skill to zoom in toward the local behavior of the polynomial functions around the zeros. So there goes the reason behind the sign analysis and multiplicity trick that we had been using from chapter 1, or as a matter of fact way back from college algebra, or even before that. Now what if we have functions given by trinomials that are not factored? Then you have to work how to factor those, and then you'll have to work through the sign analysis. How do you work those out? Excuse me. First step is usually GCF. Take the GCF out, and then the remaining part you have to use variety of trig. If it is just quadratic, go right ahead. Or sometimes you have quadratic, but fourth power, second power, and then constant terms. So that fourth power is x squared. So you can use either substitution or just use quadratic trinomial trick to factor further and do something. Let's see. Yes, here's one such example. You have to take the GCF out, and the remaining part is quadratic polynomial x squared. So you can factor further using quadratic trinomial technique, and then x squared minus 4 can be factored further. 3x squared plus 4 is irreducible, so you don't really have to do anything about it.